Functions for moments. To calculate the nth moment of a random variable x, two functions are generally used: characteristics function and moment generating function. We can see one by one. Characteristics function. Consider a random variable x with a probability density function small x of x. Then the accepted value of a function e power j omega x is called the characteristics function. It can be expressed as pi x of omega equal to accepted value of e power j omega x. Here it is the function of a real variable. The limits are minus infinity to infinity, where j is the imaginary operator. Therefore, j square is equal to minus 1. For a continuous random variable x, pi of x omega equal to integral minus infinity to infinity e power j omega x fx of x dx. For a discrete random variable pi x of omega equal to summation e power j omega xi p of xi. The characteristics function transforms the random variable x into the another real variable x. It can be expressed as the Fourier transform of small x of x with the sign of omega reverse. Therefore, the inverse Fourier transform of pi x of omega gives the probability density function with the sign of x is reverse. Hence, fx of x is equal to 1 by 2 pi integral minus infinity to infinity pi x of omega e power minus j omega x d omega. So the functions pi x of omega and fx of x and are the Fourier transform pair with the sign of the variable reverse. Moment generating function of a random variable is also used to generate the nth moment about the origin. Let us consider a random variable x with a probability density function small fx of x. Then the moment generating function of x is defined as the accepted value of the function e power vx. It can be expressed as mx of vx is equal to accepted value of e power vx, where v is the real variable minus infinity to infinity. For continuous random variable, therefore the continuous random variable mx of v equal to integral minus infinity to infinity e power vx fx of x dx. And for discrete random variable mx of v equal to summation I e vxi into p of xi. The nth moment of a x can be derived as from the moment generating function. Here the j operator does not exist. The main disadvantages of a moment generating function is that it may not be exist for all random variables and all values of v, but the characteristics function exists for all values of x and omega. Theorem: if mx of v is a moment generating function of a random variable x, then the nth moment of x is given by mn equal to dnmx of v by dv power n at v equal to 0. Let us see the proof. Consider a random variable x with a moment generating function mx of v equal to accepted value of e power vx. We know that the series expansion of e power x is e power x is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial plus so on plus x power n by n factorial plus so on, that equal to e power vx is equal to 1 plus vx whole square by 2 factorial plus vx power whole cube by 3 factorial so on plus vx whole power n by n factorial plus so on. Therefore, mx of v equal to accepted value of e power vx, that equal to accepted value of 1 plus vx plus v square x square by 2 plus v cube x cube by 3 factorial plus so on plus v power n by n factorial into x power n plus so on, where m not equal to e power 1 equal to 1, where m1 equal to e power x is equal to m1. Accepted value of x square is equal to m2. Accepted value of x cube is equal to m3. Accepted value of x power n is equal to mn, that equal to mx of v equal to m0 plus vm1 plus v2 v square by 2 m2 plus v cube by 3 m3 plus so on plus v power n by n factorial mn plus so on. To find the moments, substitute the at v equal to 0. So mx of 0 is equal to m0 is equal to 1. Differentiation mx of v with respect to v. Dmx of v divided by dv, that equal to 1 is equal to 0. 0 plus vx1 equal to m1 plus v square x square by 2 equal to 2x by 2, that 2 cancel vm2 by plus so on, that equal to dmx of v divided by dv equal to m1 plus vm2 plus so on. At v equal to 0, m1 equal to dmx of v divided by dv square at v equal to 0. Second differentiation mx of v with respect to v is d square mx of v d square divided by dv square, that equal to 1 is equal to e power 1 equal to 0. E power x is equal to m1 here equal to 0. E power x square is equal to 2 cancel equal to m2 plus vm3 plus so on. Yet v equal to 0. m2 equal to d square mx of v by dv square, where at v equal to 0. Similarly, at the nth differentiation mx of v with respect to v, we can get mn equal to d power n mx of v divided by dv power n at v equal to 0. The nth moment of x is given by mn equal to d power n mx of v, mx of v divided by d v power n, where v equal to 0. Thus the moment thus the nth moment of the x can be written from the nth differentiation of moment generating function at v equal to 0.